In chemistry, bases are substances that, in aqueous solution, are slippery to the touch, taste bitter, change the color of indicators, react with acids to form salts, promote certain chemical reactions, accept protons from any proton donor, and, or contain completely or partially displaceable O- ions. Examples of bases are the hydroxides of the alkali metals and alkaline earth metals too, etc. These particular substances produce hydroxide ions in aqueous solutions, and are thus classified as Arrhenius bases. For a substance to be classified as an Arrhenius base, it must produce hydroxide ions in an aqueous solution. In order to do so, Arrhenius believed the base must contain hydroxide in the formula. This makes the Arrhenius model limited, as it cannot explain the basic properties of aqueous solutions of ammonia or its organic derivatives. There are also bases that do not contain a hydroxide ion but nevertheless react with water, resulting in an increase in the concentration of the hydroxide ion. An example of this is the reaction between ammonia and water to produce ammonium and hydroxide. In this reaction, ammonia is the base because it accepts a proton from the water molecule. Ammonia and other bases similar to it usually have the ability to form a bond with a proton due to the unshared pair of electrons that they possess. In the more general Bronsted-Lowry acid-base theory, a base is a substance that can accept hydrogen ions, otherwise known as protons. In the Lewis model, a base is an electron pair donor. In water, by altering the auto-ionization equilibrium, bases yield solutions in which the hydrogen ion activity is lower than it is in pure water, i.e., the water has a pH higher than 7.0 at standard conditions. A soluble base is called an alkali if it contains and releases O- ions quantitatively. However, it is important to realize that basicity is not the same as alkalinity. Metal oxides, hydroxides, and especially alkoxides are basic, and counteranions of weak acids are weak bases. Bases can be thought of as the chemical opposite of acids. However, some strong acids are able to act as bases. Bases and acids are seen as opposites because the effect of an acid is to increase the hydronium concentration in water, whereas bases reduce this concentration. A reaction between an acid and base is called neutralization. In a neutralization reaction, an aqueous solution of a base reacts with an aqueous solution of an acid to produce a solution of water and salt in which the salt separates into its component ions. If the aqueous solution is saturated with a given salt solute, any additional such salt precipitates out of the solution. The notion of a base as a concept in chemistry was first introduced by the French chemist Guillaume-François Rouelle in 1754. He noted that acids, which at that time were mostly volatile liquids, turned into solid salts only when combined with specific substances. Rouelle considered that such a substance serves as a base for the salt, giving the salt a concrete or solid form. Properties. General properties of bases include concentrated or strong bases are caustic on organic matter and react violently with acidic substances. Aqueous solutions or molten bases dissociate into ions and conduct electricity. Reactions with indicators. Bases turn red litmus paper blue, phenolphthalein pink, keep bromothymol blue in its natural color of blue, and turn methyl orange yellow. The pH of a basic solution at standard conditions is greater than 7. Bases are bitter in taste. Reactions between bases and water. The following reaction represents the general reaction between a base and water to produce a conjugate acid and a conjugate base. B plus H2O BH plus plus O minus. The equilibrium constant, Kb, for this reaction can be found using the following general equation. Kb equals BH plus O minus B. In this equation, both the base and the extremely strong base compete with one another for the proton. As a result, bases that react with water have relatively small equilibrium constant values. The base is weaker when it has a lower equilibrium constant value. Neutralization of acids. Bases react with acids to neutralize each other at a fast rate both in water and in alcohol. When dissolved in water, the strong base sodium hydroxide ionizes into hydroxide and sodium ions, NaOH Na++O-, and similarly, in water the acid hydrogen chloride forms hydronium and chloride ions. Hydrogen chloride plus H2OH3O plus Cl-. When the two solutions are mixed, the H3O and O- ions combine to form water molecules. H3O plus O minus 2H2O. If equal quantities of NaOH and hydrogen chloride are dissolved, the base and the acid neutralize exactly, leaving only NaCl, effectively table salt, in solution. Weak bases, such as baking soda or egg white, should be used to neutralize any acid spills. Neutralizing acid spills with strong bases, such as sodium hydroxide or potassium hydroxide, can cause a violent exothermic reaction, and the base itself can cause just as much damage as the original acid spill. Alkalinity of non-hydroxides. Bases are generally compounds that can neutralize an amount of acids. Both sodium carbonate and ammonia are bases, although neither of these substances contains O- groups. Both compounds accept H+ when dissolved in Protix solvents such as water. Na2CO3 plus H2O2 Na plus HCO3 plus O NH3 plus H2O NH4 plus O-. From this, a pH or acidity can be calculated for aqueous solutions of bases. Bases also directly act as electron pair donors themselves. CO32- plus H plus HCO3- NH3 plus H plus NH4 plus A. Base is also defined as a molecule that has the ability to accept an electron pair bond by entering another atom's valence shell through its possession of one electron pair. There are a limited number of elements that have atoms with the ability to provide a molecule with basic properties. Carbon can act as a base as well as nitrogen and oxygen. Fluorine and sometimes rare gases possess this ability as well. This occurs typically in compounds such as butyl lithium, alkoxides, and metal amides such as sodium amide. Bases of carbon, nitrogen and oxygen without resonance stabilization are usually very strong, or superbases, which cannot exist in a water solution due to the acidity of water. Resonance stabilization, however, enables weaker bases such as carboxylates. For example, sodium acetate is a weak base. Strong bases. A strong base is a basic chemical compound that can remove a proton from a molecule of a very weak acid in an acid-base reaction. Common examples of strong bases include hydroxides of alkali metals and alkaline earth metals like NaOH and California-2 respectively. Due to their low solubility, some bases, such as alkaline earth hydroxides, can be used when the solubility factor is not taken into account. One advantage of this low solubility is that many antacids were suspensions of metal hydroxides such as aluminum hydroxide and magnesium hydroxide. These compounds have low solubility and have the ability to stop an increase in the concentration of the hydroxide ion, preventing the harm of the tissues in the mouth, esophagus, and stomach. As the reaction continues and the salts dissolve, the stomach acid reacts with the hydroxide produced by the suspensions. Very strong bases hydrolyze in water almost completely, resulting in the leveling effect. In this process, the water molecule combines with a strong base due to the water's amphoteric ability, and a hydroxide ion is released. Very strong bases can even deprotonate very weakly acidic CH groups in the absence of water. Here is a list of several strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, magnesium hydroxide 2, calcium hydroxide 2, strontium hydroxide 2, barium hydroxide 2. The cations of these strong bases appear in the first and second groups of the periodic table. Acids with a pKa of more than about 13 are considered very weak, and their conjugate bases are strong bases. Strong bases are able to form stable compounds by combining with a strong acid. Weak bases, however, do not possess the ability to form stable compounds by combining with a weak acid. Superbases group 1 salts of carbanions, amides, and hydrides tend to be even stronger bases due to the extreme weakness of their conjugate acids, which are stable hydrocarbons, amines, and dihydrogen. Usually these bases are created by adding pure alkali metals such as sodium into the conjugate acid. They are called superbases, and it is impossible to keep them in water solution because they are stronger bases than the hydroxide ion. As such, they deprotonate the conjugate acid water. For example, the ethoxide ion in the presence of water undergoes this reaction. CH3CH2O- plus H2O CH3CH2OH plus O-. Examples of superbases are butyl lithium, lithium diisopropylamide 2CH2NLi, lithium diethylamide 2NLi, sodium amide, sodium hydride, lithium bisamide 3C2NLi. Neutral bases. When a neutral base forms a bond with a neutral acid, a condition of electric stress occurs. The acid and the base share the electron pair that formerly only belonged to the base. As a result, a high dipole moment is created, which can only be destroyed by rearranging the molecules. Bases as catalysts. Basic substances can be used as insoluble heterogeneous catalysts for chemical reactions. Some examples are metal oxides such as magnesium oxide, calcium oxide, and barium oxide, as well as potassium fluoride on alumina and some zeolites. Many transition metals make good catalysts, many of which form basic substances. Basic catalysts have been used for hydrogenations, the migration of double bonds, in the Meerwein-Pondorf-Verley reduction, the Michael reaction, and many other reactions. Both Cow and Bow can be highly active catalysts if they are treated with high-temperature heat. Solid bases. Examples of solid bases include oxide mixtures, CO2, Al2O3, MgO, CO2, Cow, CO2. Mounted bases, LiCO3 on silica, Nr3, NH3, KNH2 on alumina, NaOH, co-mounted on silica on alumina. Inorganic chemicals. Bow, NaCO3, BeO, MgO, Cow, KCN. Anion exchange resins. Charcoal that has been treated at 900 degrees Celsius or activates with N2O, NH3, ZnCl2, NH4Cl CO2. Depending on a solid surface's ability to successfully form a conjugate base by absorbing an electrically neutral acid, the basic strength of the surface is determined. The number of basic sites per unit surface area of the solid is used to express how much base is found on a solid base catalyst. Scientists have developed two methods to measure the amount of basic sites: titration with benzoic acid using indicators and gaseous acid adsorption. A solid with enough basic strength will absorb an electrically neutral acid indicator and cause the acid indicator's color to change to the color of its conjugate base. When performing the gaseous acid adsorption method, nitric oxide is used. The basic sites are then determined using the amount of carbon dioxide that is absorbed. Weak bases. When there is a hydrogen ion gradient between two sides of the biological membrane, the concentration of some weak bases are focused on only one side of the membrane. Weak bases tend to build up in acidic fluids. Acid gastric contains a higher concentration of weak base than plasma. Acid urine, compared to alkaline urine, excretes weak bases at a faster rate. Uses of bases. Sodium hydroxide is used in manufacture of soap, paper and a synthetic fiber called rayon. Calcium hydroxide is used in the manufacture of bleaching powder. Calcium hydroxide is also used to clean the sulfur dioxide, which is caused by exhaust, that is found in power plants and factories. Magnesium hydroxide is used as an antacid, to neutralize excess acid in the stomach and cure indigestion. Sodium carbonate is used as washing soda and for softening hard water. Sodium hydrogen carbonate is used as baking soda in cooking food, for making baking powders, as an antacid to cure indigestion and in soda acid fire extinguisher. Etymology of the term. The concept of base stems from an older alchemical notion of the matrix. The term base appears to have been first used in 1717 by the French chemist Louis Lemery, as a synonym for the older Paracelsian term matrix. In keeping with 16th-century animism, Paracelsus had postulated that naturally occurring salts grew within the earth as a result of a universal acid or seminal principle having impregnated an earthy matrix or womb. Its modern meaning and general introduction into the chemical vocabulary, however, is usually attributed to the French chemist Guillaume-François Rouelle. Rouelle explicitly defined a neutral salt as the product formed by the union of an acid with other substance, be it a water-soluble alkali, a volatile alkali, an absorbent earth, a metal, or an oil, capable of serving as a base for the salt, by giving it a concrete or solid form. Most acids known in the 18th century were volatile liquids or spirits, capable of distillation, whereas salts, by their very nature, were crystalline solids. Hence it was the substance that neutralized the acid which supposedly destroyed the volatility or spirit of the acid and which imparted the property of solidity to the resulting salt.